Exactly. So in their proof of concept, the researchers actually implemented the CNPU and the QNPU on separate devices, reflecting those slower communication times we might see over a network, milliseconds.
Yeah.
But the key to interactivity is that the Q device is built to execute individual instructions on demand.
Kind of like a classical CPU, I guess.
Yeah, like a classical CPU. So the QNPU can send instructions to the Q device at the microsecond level.
And that allows the system to react quickly, even if the network operations are slower.
Exactly.
Okay, managing those speeds is definitely a challenge. Another one that's very quantum specific is those short memory lifetimes.
Ah, yes, coherence times.
Right. Quantum information, it's so fragile, it doesn't last very long. How does an operating system account for that
Well, that's a fundamental limitation we have to deal with right now.
with current tech?
Yes, with current tech. Quantum memories, those qubits themselves, they lose their quantum properties pretty quickly.
So QNodeOS has to be designed with that in mind.
Absolutely, to make sure operations are finished before the information is lost.
It has to be really fast.
It does. And that impacts how the system schedules tasks and manages those qubits.
That makes sense. Which leads us to the next challenge. Scheduling local and network operations.
Yeah, that one's a head-scratcher.
It sounds like even generating entanglement, which is essential for quantum networks, can't happen at the same time as local quantum computations.
In most current setups, that's right.
That seems incredibly limiting.
It is, and it's because entanglement is inherently stateful. Unlike just sending a classical bit, when you entangle two qubits, they become linked in this very special quantum way.
Okay.
And the process of creating that entanglement, especially using what's called heralded methods.
Heralded.
Yeah, it basically means you get a signal to confirm that the entanglement was actually created successfully.
Right.
It often requires really precise timing between nodes, and that's governed by something called a network schedule. The challenge is, with a lot of the quantum hardware we have today, when you're trying to generate entanglement, the nodes can't do any local quantum operations at the same time.
So it's either...
Yeah. And that's where the QNPU scheduler in QNodeOS comes in. It has to manage all of that, decide when to do local operations, when to try generating entanglement, all based on the network schedule.
It's like a very delicate dance.
It really is. And finally, you mentioned multitasking.
Yeah, multitasking.
Done in classical computing, running multiple programs at once. It's no big deal.
We do it all the time.
All the time. But why is it a challenge for quantum networks?
Right. Good question.
Well, imagine a quantum network node is just sitting there waiting for another node to finish something.
Or to send a message.
Yeah. That happens a lot in network applications.
Right.
And while it's waiting, it's essentially idle. Multitasking is about making the system more efficient.
Okay, I see.
By letting a node work on other programs during those idle times. But to do that, the quantum network operating system needs to manage everything.
The states of all those programs?
The states, yeah. And all the resources they need, like the qubits themselves, the memory, even those requests for entanglement, all for different programs running at the same time.
It's not just about sharing the processor.
No, it's much more than that. It's about managing those precious quantum resources.
So that's a great overview of the challenges. Now, how does QNodeOS actually work? What are the main parts?
We touched on this earlier, but QNodeOS has three key components: the CNPU, the QNPU, and the Q device.
Okay, let's break those down. What does the CNPU do?
The CNPU, the classical network processing unit, think of it as the brain that kicks off programs and takes care of all the classical parts of the code. When you run a quantum network application, the CNPU creates what we call a CNPU process to manage it.
Okay, so that sounds familiar from regular operating systems.
Yeah, it's similar. Now, for the quantum side, that's where the QNPU steps in.
The quantum network processing unit.
Right. So when that CNPU process starts a program, it also tells the QNPU about it.
Okay.
And the QNPU then creates its own associated QNPU process.
So each program gets its own process on both sides, classical and quantum.
Exactly. And the QNPU process keeps track of important info, like who owns the program, its ID, its current state, things like that.
Got it.
QNodeOS also has what we call kernel processes running on the QNPU.
Kernel processes, what are those?
They're like system-level processes that start up when the whole system boots. Now, the way the CNPU talks to the QNPU is by sending these quantum code blocks in the form of NetQASM subroutine.
NetQ is out.
Yeah, it stands for Networked Quantum Assembly Language. It's basically a set of low-level instructions for these hybrid quantum classical programs. Then the QNPU takes these subroutines, executes any classical control logic they have, and then it passes on the actual quantum operations, like applying gates or performing measurements or generating entanglement. It passes those to the Q device.
They're the actual hardware.
Right. And it does this by sending those platform-specific instructions we talked about earlier. And finally, the Q device sends the results back to the QNPU. So it's like a relay race.
I get it. So the CNPU sets things up. The QNPU manages the quantum side.
Yes.
And the Q device does the actual work.
You got it.
Now, we talked about the Q driver being key to making the system work with different hardware.
Right.
Where does it fit into this whole picture?
The Q driver sits right between the QNPU and the Q device. Its job is to take those hardware-independent quantum operations from NetQASM and translate them into those very specific streams of physical instructions for the Q device.
I see.
And the cool thing is, the researchers actually made Q drivers for two completely different quantum hardware platforms.
Oh, really?
Yeah, NV centers in Diamond and a trapped ion setup. And these are really different systems physically, but they can both be controlled by QNodeOS.
That's awesome.
They even tested the trapped ion Q driver by implementing and verifying a set of basic single qubit gate operations.
So they proved it works.
They did. And that means researchers don't need to be experts in every single type of quantum hardware to build applications for them.
That's a huge step forward.
It is.
Now let's go back to the different timescales and the need for interactivity. How does this three-part architecture address that?
Right. So breaking things down into the CNPU, QNPU, and Q device lets each component operate on the timescale that makes sense for it.
Okay.
You know, in their proof of concept, having the CNPU and QNTU separate reflected those slower timescales of network communication.
The millisecond.
Milliseconds, exactly. But the Q device being able to execute individual instructions on demand is really important for interactivity.
Right, it can respond quickly.
It can. The QNPU doesn't have to load a whole program into the Q device all at once, like in those older experiments.
Okay.
It can send instructions as needed, which means the system can react to things happening on the network right away.
Like receiving a message from another node.
Exactly. And in their NV Center implementation, they even found a way to interleave user-requested pulse sequences with something called dynamical decoupling sequences.
Dynamical decoupling sequences. That sounds complicated.
Well, they're basically a way to protect the qubit's delicate quantum state. And by interleaving them, they could keep the qubit coherent while still being able to execute any instruction without knowing what it would be beforehand.
So it's like keeping the quantum information safe, but being ready to act at a moment's notice.
Yeah, that's a good way to put it.
And what about managing those local and network operations? How does the QNPU scheduler juggle all of that?
The QNPU scheduler. This is a key part of QNodeOS. It manages all the processes running on the QNPU.
The user applications.
The user applications and something called the network process.
What's that?
It's a special kernel process that handles entanglement generation. Using the network stack. So the scheduler decides which of the ready processes gets to use the QNPU's local processor and the Q device at any given time.
I see.
Now, to deal with those short coherence times, they've gone with a priority-based approach.
Priority-based, okay.
Yeah, and it's non-preemptive. What that means is once a process starts running, it keeps going until it finishes its current block.
Or if it needs to wait for something.
Right, like for entanglement to be delivered.
Got it.
And importantly, the network process, since it handles generating entanglement, gets the highest priority.
That makes sense. Entanglement is so important.
It is. So when a user application wants to get entangled with another process on the network, its QNPU process is put into a waiting state, and the network process takes over.
To set up the connection.
Exactly. It coordinates with the network and the Q device to generate those entangled qubits. Once that's done, the user process can continue.
Okay, so the network gets priority to make those quantum connections, but the scheduler still tries to keep things moving.
Yes, it tries to make the most of the available time, especially when waiting for those network operations.
Now, what about